Okay, hello and welcome to the stream. So, one thing I did offline was I just grabbed a bunch of very hard Sudoku puzzles to see how our solver is doing. So, if you weren't here last time, we kind of managed to have a solver that can solve, reasonably complicated Sudoku puzzles very fast. So, just for comparison, a very basic backtracking solver solves this puzzle within 4 seconds. And this is really just a very simple backtracking algorithm. Then if we do a little bit of logic up front, we end up with sub 1 second times. This is basically just pruning the Sudoku from, nonsensical things. Like obviously, if we have already a preset number in the, input for the puzzle, then obviously we can just remove that as a possibility from all the blocks, rows, and columns. And our smart solver was able to solve this, around 100 milliseconds. Like this number keeps jumping up and down. I didn't really do proper performance testing on this, but I suspect like it's around 100 milliseconds. And then, of course, if we try to feed in very complicated puzzles into this, it will fail a bunch. So it cannot really deal with 16 by 16. It cannot really deal with very complicated 9 by 9 Sudokus. So what I kind of want to work on today is to actually try to implement more interesting solving techniques, and we'll kind of see how far we get. It gets a little bit tricky because some of the human techniques are not that easy to implement on a computer. Especially one thing I'm trying to kind of keep in this solver is like make it as flexible as possible, as in I don't really want to hard code rules that are specific for basic Sudoku puzzles, because I also want to kind of support Jigsaw Sudoku puzzles. So let's just quickly jump here. So if you don't know what these are, this is kind of how Jigsaw Sudoku look like. So you, instead of having 3 by 3 blocks, you have these, jigsaw shapes, which kind of breaks some of the solving techniques that are used to solve basic Sudoku puzzles. And I want it also to work, for weirdly size, like 12 by 12. Like this is a very strange size of a Sudoku puzzle, and so on. I'm actually liking this website because they have pretty crazy Sudoku puzzles that I can use to benchmark my solver. So I have kind of grabbed, some of the techniques that we can use to implement. We can use to solve the puzzles and can implement them in our solver. But the first one I would like to kind of show you. Let's just quickly jump to, do I have, okay. So, yeah. So let's just ignore the annotations for now. But basically what I want to demonstrate is, it's essentially a block intersection rule. So let's imagine, let's look at this column, right? And let's imagine that we have figured out that in this block, number 1 can only go here. Not like that. I want the center. So through whatever means, we have figured out that number 1 has to be in basically this section, right? Well, because this column is intersecting with this block, And in this block, we have kind of managed to narrow down the ones to be only in this intersection. That also means that in this column, we cannot have ones anywhere else. So, basically these are not a possibility. So this is this is still relatively easy to implement because we are just intersecting two blocks at a time. But this should be a pretty powerful rule and should help us solve more complicated puzzles. There's kind of advanced version of this. So if you, let's just use, let's use this middle column. So let's imagine that you have figured out that in these two, like in this area, the ones have to go here. Well, if you have done that, and basically you would do that by, okay, let's imagine that the input kind of looked like 2, 3, 4, 5, 6, 7, right? Well, if you figured this out, then obviously the ones have to go here in the bottom block. This one is much harder to implement because it's quite topological. You kind of need to figure out that, okay, like this block intersects with these two columns, and it would work the same way for rows, obviously, but this block intersects with these two columns, and there's also another block, this one, that also intersects with these two columns, and they kind of share the ones, which I'm not quite sure how to implement this in a generic way. And I also kind of get the feeling that we might be able to obtain like the fact that these ones are here from other approaches and other rules. So we will see. So for now, let's just try to do the single block intersection. So let's just, if I just do, okay, yes. So if I just clean it up, a reminder. So if we figure out, if we have two blocks in our sense intersecting. So in this case, if this column is intersecting this block, and we have figured out that the only possible spaces where a particle number can go is in the intersection, then obviously anything outside of the intersection in this block cannot have a 1. Because that would preclude, the one being here, and that would basically break this block. The great thing about this is this really works for any two intersecting blocks. So it really doesn't matter, like it would work for the Jigsaw puzzles as well, just fine. Like there's, if, for the column A, it's intersecting with the green, yellow, and blue. So I can use the same rule for that. Like if I figure out that, okay, like in blue, the one has to go, in the first column, then obviously I can remove the one as a possibility from the green intersecting with column A and from the yellow. So yes, okay. So let's go back to our code. So where do we implement this rule? So right now, let's go back to the smart solver. So the smart solver, basically loops until the entire puzzle is filled, as in as it's solved. Checks the changed blocks. If nothing changed, then we just bail out, and then we go over the blocks and call solve. So here, what we kind of want to do is look at the intersections of blocks. Yes. Okay. So we want to pick up pairs of blocks here. And we want to check if for one of the blocks there is a number that can only be in the intersection. Okay. Figuring out the intersection of blocks, that's not too hard. I think this kind of check we could implement in the block checker. Yes, so basically what I can do is, yeah, I can do it both. So basically if I had a method on the block checker, essentially okay, something like this. So from a block, I ask it to give me numbers that are fully contained within an intersection with another block. So this can be, of course, an empty set. Yeah, so this would be yeah, basically another set of a number. So I ask a block to give me the numbers that are fully contained in the intersection with another block. And if I get that, if this is not empty, I know that I can remove those numbers from the another block. Yes, yes. Okay, I think this should work. Well, let's try to implement this. So let's go to the block checker. So we will need ordered set of sure CEST. So cat interpreters and Okay. So first we need to figure out what the intersection actually is. Which okay. So yes, we just need to compare everything with everything. I don't think there's any other way to do this in a meaningful way, the way we have the blocks defined. Which I guess that's fine, like it isn't really, yeah. Um, okay. So, for our squares, that will be, I don't remember. Oh, LM, okay. I worked on this code yesterday and already forgetting everything. Crazy. So we can, yeah, auto S is okay because these are pointers. So basically I want to check if let's just use sidechain. If I have a match, then I put it into the intersection. So if I equals j, so if these are pointing to the same square, intersection insert, sure. Okay, so this will calculate me the intersection of two blocks now. So now how do we actually implement the rule itself? Well, we know that the number is fully contained within the intersection if the cardinality of the number, yeah, okay, so we can calculate the cardinality for the entire block, and we can calculate the cardinality of the number for the intersection. And if these two are the same, well, then obviously the number is fully contained within the intersection. So we can quite easily do this for all the numbers. That's fine. So basically what we want here is basically the entire cardinality. So this I want to initialize with and starting at zeros, and then the same thing for the intersection. And then I just need to calculate these two. So I just go over the squares I contain within my elements. Then for all all the possible numbers, so for all the possible numbers, we check if this square, what's wrong? What was the method? Is possible, yes. So if the number is possible, then because these are pointers. It's like really confused why this is not working. No, almost. This is wrong. This is correct. This is a vector. What are you complaining about? Oh, I guess. Oh, yeah. Never mind. I'm being silly. Like this, yes. So if the number is possible, then oh, not +1 here. Okay. And then we do the same for the intersection, which we called intersection. Okay. If again the number is possible, then we increase the count in the intersection. And now we just compare these two. So okay, and if inter cards I equals full card I, then we know the number is fully contained within the intersection, and we need the result, right? So result -1, and then just return result, right? So again, we figure out the intersection between two blocks. Then we calculate the cardinality of each of the possible numbers in the block itself and then in the intersection. And if the cardinality is the same in the between the intersection and the full block, then obviously all the possibilities for this number are contained within the intersection. So this is one of our numbers we care about. So since we have this, we can now in the smart solver so we can just do this the dumb way, or we can actually be a little bit smarter about this, because I mean obviously not only some blocks can potentially intersect, and most of the blocks will actually not intersect in any meaningful way, because if the blocks only intersect in one number, and like if that is the case and this rule would apply, that would also mean that that's the only possible space for the number. So that would have been picked up in the solve because that would be a next naked single, right? Or technically hidden single, I guess. Yes. So in this loop, we would pick it up, and then basically in the next iteration, because this number would be set, it would just easily propagate. So we really only care about intersection between rows. Yeah. Intersection between rows and the 3 by 3 blocks, and intersection between columns and the 3 by 3 blocks. Yes. But I have no good way to check that. um, I mean, okay, I guess it's fine to just do all blocks against each other for now, and then we can come back and try to optimize this. But there is one thing to mention. We really do only care about the change blocks. But I guess in this case, the changed block can either be on the left side or the right side, right? Like, actually not, right? Because this is kind of like one block is forcing the number onto the other. So we only really care about the change blocks being on the left side of this operation, because that's the case where finally the number is contained, because something changed and suddenly the number is contained within the intersection. And the block that would have to change for that to happen is the one that's on the left side of the operation. Yes, okay. So we want to have the outer loop across the changed blocks, but then we need an inner loop that actually goes through all the blocks. Um, we need a new method. We need a new method that will just give us all the blocks. Change blocks. That's in Sudoku. Okay, so yes. Oh. No, I guess that's okay. So we can just have we can just return a const reference. That's fine because this will be on the right side, so that's okay if it's a const reference. Um, so I will just put it here because that's fine. And now we can do blocks here, right? So this has to be a const reference. So now what I can do block get intersecting numbers with our block. So this gives us the list of the numbers that we need to remove from block. No, wait, the other, what? Yes, the other way around. This is the list of the numbers that we should remove from our block. So this cannot be a const reference because now I need to mutate the R block. Yes. Yes, indeed. So I need to change this. So not const. And actually optimally, oh yeah, okay, I already have a prune. So what I can just do here is this. Number. But I guess I should quickly check. I don't think this actually line up. So get intersecting numbers. What is it actually returning? Oh yeah, we insert I plus 1. So okay, so this is actually returning the numbers as in numbers, not indexes, which is good. In that basically means this should work. What is it complaining about? Sure, there's a typo. Yeah, okay. um yes, so again, what we do, so let's just mark this. So this is intersecting blocks rule. So we look at the intersections of blocks, and if there are any numbers that are fully contained within the intersection from the left block, so the only possibilities where the left block can put those numbers is in the intersection, then we need to remove, oh no, this is wrong. Because this will prune them out of everything, not just, we want to remove them from the spaces that are not in the intersection. Okay, so in that case, we should basically implement it here. Yeah, okay, let's just change this. So let's just call it prune intersection. So then we need to take this one as a reference, not a const reference. Yes. So we will not be modifying the, so this will still be const because we are modifying this block that we get passed. So we figure out the intersection, and basically now what we want to do is instead of storing it, we want to go over the content of the right block. Well, maybe it's actually better to just complete this first. But then we want to go Uh, then we want to go over the squares contained within the right block. We want to avoid stuff that's in the intersection, so we need to go over the intersection. So we want to skip over the stuff that's in the intersection. But then if it's not in the intersection, yes, then we want to go and remove the stuff. So remove number, right? And now this is not returning anything anymore. Yes, so this will be, yeah, let's just leave it like this, that's fine. Right. So again, we calculate the cardinality. If the cardinality is the same, remember the number. Then for everything that's not part of the intersection, we just remove those numbers as possibilities. Okay, then in our smart solver, we just want to do block prune intersection block, and that's it. Okay, let's see. So we didn't break the old solver, I guess. But it looks like that this is still not enough to solve the hard puzzles. Okay. Actually, I mean, I'm curious. So let's have a look at some of these. Actually, I should update this, but let's play with these now. I'm curious to look at the debug print for these. Okay, this doesn't look that that much solved. So yeah, our solver is kind of not able to make much progress here. One, two, five, six. Hmm. Kind of wondering. So, one thing I want to do at some point is to also work on some UI for this. I'm kind of wondering if I should prioritize that because staring at the text output is not super useful. It's kind of hard to see if this is indeed stuck or if something is wrong. Um, I mean, I guess we could just try to feed a bunch of easy puzzles into the solver and see if it breaks at any point, or if it solves the Sudoku in like a weird way that actually isn't consistent with the solution. I mean, there's definitely one thing we could do. Um, I wonder. Like these are all kind of similarly. Well, this one looks more progressed than the other ones, at least. Yeah, there's like a lot of localized stuff down here, like this like the bottom middle 3 by 3 square is very unsolved. But otherwise, like there actually is a lot of progress here, right? Like we have a triple, well, that's actually a quad. So 1 2 8 9 1 9 2 8. Yeah. Yeah, and there's a similar situation, like for example, here is 1 2 3 1 3 8 3 8 9 2 8 2 8 9. Uh, so yeah, there's like not a good way to figure out where those actually go. Okay, so we need to implement more stuff, obviously. So let's have a look at what we could do. Um, the unique rectangle, I don't think that one would actually help here. But this one, I thought I could actually implement reasonably easily. So unique rectangle kind of actually might be better if I again just like demonstrate it on this UI. So if we have a situation that we have something like this, uh, so what can we say about this square now? Well, let's think about it. So if this is a 3, then this has to be a 4 then this has to be a 3, which means this cannot be a 3. Oops. What the heck? So this cannot be a 3. If no, am I doing it wrong? I think I'm doing it wrong. Oh yeah, sorry. They need to be still contained within the blocks. I did it wrong. No. Uh, right. Yes, sorry. So, so in the unique square is this thing cannot be a free 4. Why? Well, in a normal Sudoku, and this is one of the issues, like this will only apply to symmetric Sudoku puzzles, which like if you put in like more interesting stuff, this will basically break. This kind of situation can never be disambiguated. So because it's symmetric, if I put a 3 here, the 4 has to be here, and these two follow. If I put a 4 here, 3 has to be here, and these two will follow. And it will not matter what, like, which one I put where, because basically there can never be this kind of symmetric situation. So what you can then do is, obviously, if we had the 1, 3, 4, well, we can just remove the 3, 4, and this will be a 1. But this only applies to like normal symmetric Sudokus. So this will work with the diagonal Sudoku. It will not work with the Jigsaw Sudoku, I think. It will definitely not work with the killer Sudoku, because those are definitely not symmetric. And I don't think it will actually also work with chess Sudokus, because those are also inherently not symmetric. I mean, not in this way. Anyway. Yeah, so probably this is not a good thing to implement. We can have a look at Swordfish, but this will be a nightmare to implement. Um, so hmm, I wonder. We could do an X-Wing. Can I figure this out from my blocks? I mean, this only talks about rows and columns. So this should pretty much work for any weird variant of Sudoku as well. But this is a very tricky technique because like basically you are trying to find two rows or two columns that kind of share the positions of a possibility. So it's kind of like a pair, but like in a weird way. Uh, so we would have to so we would have to have an explicit knowledge what are columns and what are rows, right? And then basically we are trying to find two rows. Yeah. We're trying to find two rows that share the possibilities. Okay, so first of all, we can filter out any rows. So we only have to look at numbers that have two options, two possibilities. And then we basically try to find a matching block that has the same two possibilities. Guess we could do that. Like we would have to introduce the knowledge what is the type of a block, because we really want to only match rows against rows and columns against columns. But that wouldn't be too crazy. Um, One thing I'm not sure though is if this would be helpful. Like there's a 5 and a 5 here. Mm. Yeah, and moreover, no, it's not just the type of the blocks actually. So, because what the X-Wing actually gives us is if we figure out that, okay, like we have this row and this row that have the 4 at the same positions, then we want to remove the 4 from these two columns. So we basically need to have a way to fetch a column block by its index. I guess that's still fine. I'm honestly not sure if there is a Sudoku variant that messes with the rows and columns. That's one thing that I'm definitely not quite sure. I haven't seen one yet, I don't think. At least, like, if I have, I don't remember. So can we just say that we always have rows and columns no matter what, and just have those as like addressable by the row and column index without like losing flexibility to implement stuff in the future? I guess that could work. Okay, let's try that. So let me just write it down before I forget. So implementing Xwing. So want to find parallel blocks. So this is either rows or columns that have only that share a number possibilities, or how I don't know how to formulate this sentence. Yeah, so they basically share the possible positions of a number that has only two possibilities in those blocks. Um, yes. So we need get row, we need get column. Thinking about these more advanced rules, like we are kind of, I think we need a new prune method. That basically you can pass in a whitelist of indexes that you don't want to touch. That would have been actually helpful also for the intersecting block rule, where we basically want to remove a number except from the intersection. Yeah. So you basically try to match up. Well, okay, we can filter for the rows or columns that have actually do have a number. Okay, so we kind of want to have a method on a block get numbers by frequency or some such thing. Then, so if we do this for all the rows, then we basically try to find rows that actually intersect on some number, because obviously if they don't even intersect on the number, there's no point in checking the positions of the number. And yes, we really only care about numbers that have two possibilities, because that's the only thing it will work with. Yes, we could do this. We need to really change the way we represent the blocks in our Sudoku puzzle, so we are actually able to fetch them by row and column indexes. But it should work. But I'm definitely not confident that this will actually help us solve the more complicated puzzles. I mean, we have some pretty, like here, for example, the 8 is only 2 positions. But I don't like see a good matchup for that. That would actually be useful. Yeah, there's like 3 possibilities in this column. Yeah, it is tricky. I mean, there's also the swordfish, which is kind of a it's basically an extension of an X-wing. Let me just remind myself how the heck this works, because this is something I never use ever. Yeah, so it's basically a generalization. So we can, instead of looking for doubles, so like instead of looking for two blocks that share a number on two positions, we can look for three blocks that share a number on three positions. Which in this case, yes, like the fives on this row can be here and here, then here on this row they can be here and here, and then on this row they can be here and here. So these three rows together form the generalized X-wing. So that means that in the affected columns, we can remove the fives from the other positions. Maybe, like, we could maybe generalize this completely. Like, the moment I'm implementing, like, I either implement just the X-wing, or I just go for a full swordfish without any, like, limitation, and go up to, I guess it's again 8, the size of the Sudoku divided by 2 number of blocks. I think I don't have to care about bigger sets. Maybe, I'm not sure. Um, well, okay, how would I generalize this? So we would get the numbers by frequency. Then basically look at the union of the positions. And okay, I'm getting somewhere. So in the generalized version, we grab X number of blocks. We look at the positions of a number, and if the union of the positions, if the size of the union of the positions equals X, then we have a swordfish. Right. So we would, do we even have to do the get numbers by frequency then? So if we just go over, okay, so if I go back to the code for the doubles and triples and whatnot, right? So here I'm creating a set of squares, right? Well, what the swordfish is kind of doing, it's creating a set of blocks. And then basically what I want with the set of blocks is for every number, I want to check if, yes, if the union of the positions for that number is the same size as as the number of elements in the set of blocks. So it's kind of the same logic as this, actually. It's just that I'm creating sets of something different. Like I was here, I was creating just sets of blocks, sets of squares. Now I want to create sets of blocks. But actually the logic itself is pretty much exactly the same. Yeah, I like this. This would mean that we don't have to implement X-Wing at all. We just jump straight to Swordfish, and we can kind of do a very general Swordfish that just works every time. I still need to have the code for like narrowing down what are columns and what are rows. But that's okay. Like that's not a big deal. Yeah, okay. I will do that. But before we jump into that, I definitely want to take a short break. Um, so I will be back soon. Okay, and I am back. So, one thing I kind of realized is if I look here, like the code that actually generates the sets for me to check is always the same. So, and it will be also the same for the swordfish approach, right? So, I kind of want to generalize this code a little bit and then basically switch over these two over to the generalized code and then just reuse that to get my swordfish sets. So, right. Um, so what does this boil down to? So we get, so we always want to get out a vector of, yeah, so this is a set of like, yeah, set of sets basically, vector of vectors of indexes, right? So that remains always the same. So yeah, let's just start writing this. Then the thing we are iterating over, that's the thing that changes. So here it's, we are creating the sets out of a vector of squares. Um, so that's the parametric part. It will always be a vector though. So it will always be a const std vector, but it will be of t star. Um, and we will always have the size because this is the size of the set we are trying to find. Right. Then, yes, the consumed path and first index, those are just internal things. And I'm actually thinking to make this a little bit less clumsy and just make these part of the internal interface. So basically now, oh, come on, what the heck? Right. So now what I do here is just I return, well, this is always a void, so that's fine. But I do result, lm's size, and here I just set the default parameters that I basically have here, so I just hide it from the interface, from the external interface, I mean. So yeah, so this would be a 0, std vector size t, yes, and first index. Yeah, not first index, 0. Okay. And then this is the thing that we actually have the logic, right? So then I think the logic is always the same. But we'll probably maybe might need some extra stuff. Let's see. So first index to alarms.size. Okay, that stays the same. Okay, so this piece of logic this is actually the part that makes basically the two bottom functions different, right? Like, yes. Mm, so I think what we need is basically take a function here that will look at the potential set and will just give us a boolean if the potential set is valid or not. And if it is, we just put it into the result. Yeah, we basically do this. So essentially is valid set. So what heck do we give it? We okay. So we actually first need to do this, and then we do is valid set R. And I guess it needs access to the LMs. Yeah, something like this. So we construct the set, which is the path until now plus the current index. We call the isValid set, which is a thing we don't have yet, but basically this will check if this satisfies the whatever constraints we are looking for. If it does, then we just put it into the results. And here we just do this. Right. That looks correct. So now I need to somehow get this thing in here. So it will be std function returning a bool, taking as a parameter std std vector t star and std vector right. So reference to the elements and reference to the potential set. Is valid set. And I think we want a reference to this. I mean, technically const reference. Because we don't want to really be copying this around since this is a recursive function. I don't think. Okay, so then we just plug it in here as well. Okay, so let's try to rewrite. Let's try to rewrite these two using the generic version now. So again, this takes as a parameter const reference to this. And const reference to the set, to the potential set. Actually, let's just okay. Let's just do it this way so the formatting doesn't go completely mental. Right. What do you not like? Okay, I guess I can force you to be square type. No? Wait, what? Why don't you like this? What? Oh, it doesn't like the function. Oh, do I need to take this as a value in this one? Yes, maybe. Just that's strange. I think that should just work. I mean, std function can be. If I just do this, well, not t, obviously, square type. Wait, I should be able to create a std function out of a lambda. Or am I missing something? Um, okay, I think I know what's the problem. Are you happy now? Yes, okay, so that, yeah, that was the issue. Because I wasn't returning anything, it was returning void and complained about that. Yes. That actually makes sense. So, yes. So this is my check function. So what the check function will do... I need the size as well. No, but the size is obvious from the number of elements in the set. So set.size. TMP union. So this will be lms.size, right? Set to empty set. alarms. Okay, so this was here only because we had the partial path. So now, because we have the full set already, I can just do that. I suspect this is okay. Well, the good thing is we actually did write tests for this. So I should be able to just, I need to switch the header, but other than that, so if I just do this, well, actually, let's just do both of them. So I will not be deleting the old code, but I just want to kind of redirect the old code to use the new code instead. So this old one should go away for now. And then we want to do the same thing with this thing. Where, okay, this again goes away. And the same idea happens here, except what we are doing here is different. Yes. So let's just put the code here. So again, the size is set that size. I'm just gonna wait. So alarms size set to empty. We go over the numbers. Numbers is the set. X plus 1. So this can go away because we have the full set. Then we count the squares. So this is alarms. Yes. Has intersection with that. Count squares plus plus. Yes. Like that. And this piece of code can go away for a bit. And if I didn't screw up things, technically if I run the block checker test, it should work. Okay, some issues. Generic recursive find. Width is what it said. Yes. Oh, why is the formatting exploding? This is so strange. That was a mistake. Yeah, I will need to play with the configuration of my ID because this is very annoying. Quite sure, but it sometimes decides that the formatting should just explode. I mean, it should fix it in the reformat step afterwards, but yeah, see, it fixed it, but I don't know why it sometimes just decides that, yeah, things should just go weird. Okay, let's see. Does it compile now? Yeah, okay, so it does compile. Does it still pass? It passes. Okay. Um, so that means these two things don't work. Okay. So now we have a generic recursive find. So we just need to use it on the blocks now. And I can get rid of the old code because now I know the new code is actually working. Right. So again, we need to first so how do we do this? I mean, one way would be that instead of just having a vector of block checkers, we could have two special vectors for the rows and the columns, and then have a vector for everything that's not rows and columns. That does make rows and columns very special, but I don't particularly have a problem with that. Like, that's kind of okay. Hmm. Yeah, I think that will be the easiest way to do it because, like, alternatively, what I could do is basically have an enum inside of the block checker that essentially describes what kind of block it is. But like block checkers, I kind of want to keep for for blocks that are the same size as the Sudoku puzzle. So for for 9 by 9, I want block checker to only cover blocks that are 9 squares. They can be whatever shape they want to be. They can even be like completely distributed across the puzzle. There's like some color Sudokus that do that. But I kind of want to keep these to be just for the size 9 blocks in a 9 by 9 Sudoku. Because, like, okay, so let's jump to here. So this is one of the types of Sudokus I would really like to implement afterwards. Like if once we get solver that actually works. Okay, so one thing I have been kind of skirting around is the problem we are having, as in the solver is not solving the puzzles, is trivially solvable by just re-adding backtracking. And that will actually not make our solver slow. I just don't want to do that because I want to kind of reach a point where we have a solver that works like a human and never makes guesses, which is not something you should need to do to solve a Sudoku puzzle. So I kind of want to reach that point. We can always kind of lean into the backtracking as a kind of last resort, but I would very much prefer not to do that. Anyway, so killer Sudokus, essentially what happens here is you have the normal Sudoku setup with the 9 blocks, each of 9 elements, But then on top of that, you have these sum blocks. So these are still blocks, as in within this block. Okay. So within this block, I need to have unique numbers. I cannot repeat them. Well, this is a bad example, but let's take something that's actually crossing. Well, shoot, this one doesn't really have those. Let's go back. Let's pick one that actually has some interesting stuff. Right, okay, so this one, for example. So if you look at this block in particular, I could put a one here and one here, and from Sudoku perspective, that's totally fine because this is a different block than this. But since this is also a block, I cannot do that. So these still kind of behave like blocks, as in you can still kind of use the same pruning algorithms to look at them. It is just that they, on top of that, and being weird sizes and weird shapes, they also give you the sum of those elements inside. And this particular interface also gives you like, okay, like for a 26, these are all the combinations that make 26. So yeah, like for these kind of blocks, I kind of want to have a different type. I might reuse like a lot of the functionality, and I might even, have those types be like inherited from the same base type or something. But for block checkers, I'm kind of really thinking that those should really be just for the proper blocks. But they can definitely be Jigsaw, like that's fine. But here in the Jigsaw, like this still has 9 spaces. Okay. Yeah, yeah. Let's just do this. So we move forward. So standard vector of block checker. So this will be row checks and column checks. Now the tricky part is I need to basically adjust all of these. Or alternatively, we can still have checks be all blocks, but then on top of that, yeah, that might be better. So on top of that, we will just have an extra data structure that will store pointers to the blocks that are rows and columns. Because that way we don't really, like if you want to just like go over all the blocks, we still have the possibility. We don't have to reintroduce some functionality. But if we specifically want to talk about rows or columns, we can. Yes, I think that makes the most sense. So going back to the Sudoku row checks, so I think block checker, yeah, so block checker is just straight up block checker. So these will be pointers. Then basically here, what I will need is some getters for the columns and the rows. Um, and yes, then basically I just need to make sure I initialize them, which happens in setup checkers. Yep. So checks row, and I'm already storing in the block mapping. So now just I need to do row checks, pushback with the same idea as the thing here. And the same for the columns. So call checks, pushback, and this thing. Okay, so now I can access specifically the blocks that are rows and columns. I have the generic set generator thingy. So now I just need to put it together. Okay. Well, where do we actually put this? So it doesn't really make sense to put it into the block checker because this is operation on top of block checkers, I guess. So I guess it should be inside of Sudoku itself. But this is the place where I had the generic recursive find, right? I mean, I guess I can put it here, but then I need to call it from Sudoku. Yeah, I guess. Okay. So what are we trying to look for? So this is swordfish. I have written this down somewhere. Yes, okay. We grab X number of blocks. We look at the positions of a number. And we kind of want to do this for all the numbers, I guess. If the size of the union hmm. So do we want to do this? Do we actually want to do this for each X and each number? Probably we do. Yeah, I mean, how else would we do it? So I guess the function here can be for a specific size and a specific number. Yes, okay. So now the question is, what the heck do we actually want to return as the set? I mean, if I just return the set of the blocks that are in a swordfish, I guess that's enough because because so besides number, uh, if I just return the blocks that are in a swordfish, based on that, I can figure out. Yeah, I can easily figure out the positions. It's a little bit awkward. Like the way I kind of abstracted this function, it's not optimal for swordfish because we would kind of want to immediately prune the columns, but it's kind of hard to access the columns from here. So we kind of need to return. Oh, but that's actually fine. So we return all the combinations of columns or rows, right? So all the combinations of blocks that are in a swordfish for this size of a swordfish and this number. Usually that should be just one set, but technically it can happen, like there's nothing preventing this from happening multiple times. Then we go over these and we go over them. We figure out for each of these sets, we figure out the all the possible positions of the number, which tells us the columns we need to clean. And then we just remove the excessive possibilities from those columns, yes. There are not these indexes. Oh, geez. If you are watching this and you are not confused, I congratulate you. You have a beautiful mind. I'm already so freaking confused by just thinking about this. But yeah, feel free to ask things in the comments and I will try to answer as much as I can. But yes, this stuff is getting very complicated. But that's what Sudoku is. Like it's not an easy puzzle for sure. So okay, we go over blocks. So this will be either rows or columns for particle size and particle number. So blocks, block checker, right? So here, when do we want to return? We need to capture number in our lambda for sure. So a set of blocks is in a swordfish if the number of positions across those blocks for a given number is the same as the size of the set. So we kind of want this is okay. Set to empty. So we want to so the x no wait yeah, so the x is an index of a block. So for that block we want to find all the positions of a number. So we want to go over all the elements inside of the block, all the squares inside of the block. So this will be lms x Uh, we don't have a way to get at the squares inside of the block checker. That's annoying. Yeah, okay, let's just make this closed std vector square type. And yes, I will need to have like one stream where I just do a cleanup, because the interfaces are getting very, very hairy. Squares. Right. Square type, get squares, right. Uh, so going over all the squares, and I can do this because these are pointers. What are you complaining about? Do you want a pointer? Yes. Okay, so going over all the squares. If, yes, if this is possible, oh, I want to, this needs to be a normal for loop because I really want to remember yeah, I really want to remember the position because that's really what I'm looking for. Is the positions number. Okay, so this is that's better. So squares I is possible the number. Then I want to TMP. So this would be not TMP. This is positions, right? And this I'm kind of misusing the. Actually, this is kind of stupid. Let's just use an unordered set. Right. So positions insert I. So okay, again. The blocks are in a swordfish if in a swordfish for a given number, if the total unique positions across all those blocks, unique positions, right, for the given number are the same as the size of the set of the blocks. Right. So I want to return true if position size is the same as set size. Right. I go over the set of the blocks. I record the positions of the number And if all the unique positions are the same size as the size of the set, then yep. Okay. So I think this should work. Uh, but okay, like this is getting very, very complicated. Um, how the heck do I even test this? Um, yeah, okay. I will really need to test it in the Sudoku test because again, this is more related to the Sudoku not than to the block checker. I just had to put it here because the basic template is so the basic find is templated. Actually, I should just move this out completely. Like they have no reason to be in this file. But okay, let's just not get bogged down in those details. Mm, right. So let's try to prepare a test for this somehow. So I kind of want to prepare a test that has some swordfish situations. Hmm. But that's not easy. Um, I mean, alternatively, we can just like flip the coin and come back later and just try to use it in our solver. Okay, yeah, let's come back to the test later. Or if this, I mean, later, or if this doesn't work. Um, so the X-Wing is off. We are doing swordfish. So for swordfish, so we said we want to iterate. Um, so we want to go from size 1 to um, why don't I have, wait, yeah, I don't have size method on my Sudoku, which is kind of strange. Um, size return. Uh, wait, I don't even store the size. Yeah, because the size is always kind of implicit. Well, I just make it explicit. Put it as the last thing. So right, and the same here, except here the size is data, like size. Um, right. Oh, did I? No. right. So then in here, we can go Sudoku to Sudoku size divided by 2. That's unequal, yes. So these are the sizes of the swordfish. And then we go for each number. So this will be 1, 2, size. We do recursive swordfish find for okay, yes, we need the result. So result. So result. Oh, come on. What's the? I want to see what's the interface. I've forgotten. So blocks. So okay. So let's do first columns. That's fine. Then the size is I and j is the number. Right? Yes. Then we will want to do the same thing for the row, but in between we need to process results. Okay. So to process the results, what we need to do is the affected rows, and here it will be the affected columns. Remove number from all rows, sorry, columns not in set, right. Okay. No, I've been going for 2 hours already, so I think I will just try to finish the swordfish, and that will be good enough for today. But I will just go for a short break. I will be back in like 5 minutes. Okay, so what we want to do here is effectively the same thing we do in the actual swordfish search. So we want to figure out these positions again, which is unfortunate, but yeah, like it's just the way I brought this. Like there's no way around this, unfortunately. Um, but that's okay. So I figure out the rows that are affected, which will be I go over. Okay, so this I actually want to do for each of the results. So for um, yes, so for each of the results, so for each of the swordfish instances, I want to go over V, which is the set of the indexes. Uh, so this is Sudoku.get. Which one is it now? So I'm looking at. Okay, so I should be looking into the columns. So first I fetch the columns. Yes, so for each of the column in the set that's in the results, if number is possible, number is J, rows insert, I need the K here because we're running out of letters. So squares K is possible, J insert K. No. Yes. Oof, jeez. Horrible code. Like this is getting nuts. It's like a four cycle. This is 4 cycle deep. Oh jeez, what am I doing? This would, yeah, this will need a massive refactoring afterwards. This is just getting crazy. So okay, after this thing is done, I have the list of rows that are affected, and V is the list of columns that where I want to keep the number. So now what I want to do is I'll loop over the affected rows. Yes. And um, and for the squares inside of the row, if it's not part of the columns that I shouldn't touch, yes. Wow. Oh no, not this v dot size. Yes. Um, plus plus if VL equals K okay, right. So we skip if this column is one of the columns that's in the set, not this set, this set. And if it's not, then we want to, for Sudoku get row blocks, R get squares K remove what are we removing? The number, and the number is J. Yeah, I need to write some comments here because this is just getting insane. From the row in columns that are not part of the set found swordfish set, remove the number, as a possibility. If this will work, I will be truly amazed because this code is insane. I don't remember where I wrote code this complicated. So, funnily enough, you want to do the exactly same crap, but for the other dimension. But before that, you want to do result.clear. So we need, okay, so we loop over the results. Calls for the affected columns, remove number from all rows, not in set. Yes, that's basically what this is. So calls.insert. So this figures out the affected okay. Right. So when we loop over all the columns, in those we go over all the rows, we skip rows that are part of the result. So this will be get call blocks. So it should be get row blocks. Yes. Get call blocks. In the current block, that's a column, get all the squares. That's the K. Remove J, which is the number. From the column in rows that are not part of the farm sources chat, removed. Yes, okay. Whew. Does this even compile? Yeah, it does compile. Wow, I'm impressed. Does this run? Not. I was compiling the wrong thing. Okay. Does this compile? It still compiles. Okay. Does this run? Nope. That's all broken. Wow. Okay. Somehow it didn't break. No. Okay. It broke even the simple puzzle. Jeez. Yeah, I will need to refactor this because this is impossibly complicated. Um, I need to write some helper functions. Like for example, I need a helper function that just gets me a positions of a number in a row or column. Actually, don't I already have that somewhere? Um, no. Actually, let's do that. Well, I was thinking about finishing the stream, but let's do a couple of more things. Let's do number positions on the block checker. Which will basically do, where was it? Yes, this thing. No, wait. Oh, this thing. Yes. So let's put that here. So I just loop over, yeah, over my elements. And if my elements, the number is possible. Oh, yes. So this obviously needs to take the number as a parameter. Yep. Then positions inserts, return positions, and I think I need like an alternative interface here. So number positions like this. Because this is actually what I need to call from the recursive function. Yes. Okay. So now I have this. So What was that? Yeah, okay. So here again, I kind of deleted what I didn't need to delete, but that's fine. So for size t, we set at v number positions number std set size t, right, like this. And if the positions is the same as the set, then we are done. Okay. So this was slight improvement. Then I can kind of use the same logic here, where I'm trying to figure out okay, so this is rows, right? So then I go over these. So Sudoku get call blocks x number positions j rows. Right. I think I really need a block level prune that skips over things, because this is a function that we have done multiple times already. So, but actually I have this thing somewhere else also here. Okay. So one more time this, so this would be Sudoku get row blocks x number positions yes. Okay. Then let's create prune on a block checker. So I already have a prune. So what I want to have is prune with a whitelist. So right, like this. So remove the number from everything but those indexes. Right. And actually the prune, where the heck is it? Right, so the prune can actually call the new prune with number and an empty vector. Right. So now I do this, but here I will have a skip is false, and for CEST list if I equals whitelist j. So if the thing is whitelisted, then skip equals true, and then if skip equals true, then continue. Right. So then we can simplify this code. So this will just be Sudoku get call blocks are prune um, j is the number and the whitelist is v. Okay, and the same idea here. Okay, this is already much more readable. Um, did I by chance fix it? I doubt that. But I mean, let's try and see. Miracles do happen from time to time. Oh wow, I actually did fix it somehow. Well, okay, we made our solver much slower, but like 2x to 3x. And we are still not able to solve these complicated Sudokus. So okay, like it's not enough to use swordfish for these Sudokus. That's wow. um, I mean the 16 by 16 is looking better and better, but still nowhere near anything useful. I should actually compare whether the swordfish did anything for these. That would be kind of interesting to see. Um, I'm really wondering, like, what do we need to implement for these Sudokus to be solvable? And I mean, again, like we can easily solve these Sudokus in a very fast time by just doing like reintroducing backtracking. But I'm really trying to avoid that. I'm really trying to get to a point where the solver will actually solve these just by using the human techniques. Okay, I think that's good enough for today. I think the next step will be actually making sure that the more complicated techniques actually work. Um, we know that Well, we test at least the which one was it? The solve, at least partially, that's looking for the different size sets. Mm. But I really want to make sure that we don't have like any hidden bugs, because the code is very complicated, unfortunately, and I mean, it is what it is. Like, we are basically keep looking for permutations and playing with those permutations and so on. So like, there's no way to make this code simpler inherently. Like, it is what it is. Like, we are kind of looking for sets, and that kind of means that we need to have nested loops all over the place. But I really want to make sure that we don't have any bugs in the code, because just from like staring at the results, like, I, there's no way for me to tell if it's working or not. Yep. Okay. So what do we, where do I have the state thingy? Here is the state thingy. Okay. I guess this would be version 5. So what can we do? We can solve easy Sudokus. We implemented set. So this is inside block set finding. We implemented block intersections. We implemented swordfish, and what we need to do is, very obviously, we need code cleanup. We need tests for block intersections and swordfish. I've given up on that. Yeah, okay. So inside of the code cleanup is, we need to really think about like what to extract as like helper methods on the different data structures, so we don't basically have to write these for loops all over the place. We need, yes, this is definitely a thing we still haven't done, is either get int xy or operator square brackets to get to square. And this actually applies to multiple things, like we keep just returning the internal data structures, like the vectors, which is makes the code very hard to read. We actually don't need to encapsulate the server class, like that was the thing I wanted to do initially, but now that we have the old solver and the small solver, like that actually, like it works as a function, that's fine. We don't have the puzzle data representation we might want to think about that because this would help testing. So we might want to think about how we want to represent the Sudoku data in what data format, because if we have a data format, then we can basically prepare a test suite where we have just the, puzzle inputs and outputs, expected outputs, and just have a big test suite that just runs through all the puzzles. Um, okay, this goes away. Okay, I think that's it for now. And yeah, like next week, yeah, again, I don't think we'll be implementing anything new next week. We just really need to clean up the code, and I need to think about. So there's still. We didn't do the unique rectangle. That might be a thing we don't really to implement this one. But maybe, who knows, maybe we need to. We have swordfish, which means we have X-Wing as well. We might need to implement the XY wing. Maybe. Yeah. Again, I'm really trying to avoid like solving techniques that are very specific to normal Sudokus. Um, there's yeah, there's like these kind of general techniques, basically forcing chains where you have a chain of things that kind of force numbers into a particle sport, or like force not a possibility in some spot. This is reasonably generic thing, so maybe we should implement something like this. Yeah. Yeah, I will need to think about it offline, and maybe read up on like more interesting solving techniques that I don't really use but are actually good for machine solver. Because I mean, honestly, like for example, I would not use swordfish. Like that's such a weird thing to actually notice in the Sudoku, that like as when solving a puzzle, I would never basically use that. I might use X-Wing at some point. Like it's that one is kind of easy easy-ish to spot. But yeah, like there's definitely difference between what's easy to use as a human and what's easy to implement into a solver. But yeah, I mean, what that means is there will be many more sessions of this live coding thingy. So I have stuff to do over weekends. Good for me. Well, anyway, um, have a nice remainder of your day. if you are watching either the stream or the recording, or have a good night or good morning or whichever applies, and see you next time.